So first, I want to thank the organizer for inviting me to come in here. I will talk about the epoch reionization and 21 centimeter observation. Actually, we don't have observation yet. We have some little observation, but mostly it's a prediction for the future. As you know, during the Big Bang, the universe is ionized, but then after the Big Bang, it goes into the gas goes into a neutral state. But once the first generation of stars begin to form, these stars will emit photons with energy greater than 13.6 eV, so that they ionize the gas again. So this is what we call the reionization. So this epoch of the universe is still being studied. We still have a very little understanding of this epoch. So we currently have a number of information obtained indirectly. So first, from the cosmic microwave background. So the cosmic microwave background photons typically last scatter at the last scattering surface. But then these photons will propagate to us. And during the propagation, some of them get scattered by the ionized electrons, the electrons in the ionized medium. So from the observation of this CMB and isotropy, especially its polarization, we get some information. We have some telescopes right now, for example, the Hubble Space Telescope, which takes very, very deep image of the sky, and we obtain some of the image of the brightest galaxies during the epoch reionization. But we only see the tip of the iceberg because most galaxies are much fainter at that time, so we cannot really see them. Although with the JWST, which will be launched soon, in 2 years, maybe we will get even better, but still we will be a long way from getting to the bulk of the star-forming galaxies at epoch reionization. So currently we actually look at some of the quasars, high-redshift quasars. Their spectral line have these so-called Gambitson traps, which is that the gas, the neutral hydrogens in the gas will strongly absorb these photons. So at this high redshift, we see that almost all of the photons get absorbed. So that tells us there's begin to see at redshift 6 some neutral gas, and that shows the end of the reionization. But still, even if only 1% of the gas is neutral, this will be sufficient to absorb this, so we can still cannot see them. And we also look at some of the metal poor stars locally. These stars, if they have very, very little heavy elements, then they are probably produced very early time, so that their element pattern tells us something about the early universe star formation. But still, all of these are kind of indirect. So we do want to have a direct probe into this epoch reionization using the so-called 21 centimeter line. So here shows that what we expect. During the epoch reionization, we will see this kind of three-dimensional distribution of the gas, where some gas are ionized, some are remains neutral. Now, after the reionization, of course, most of the universe are totally ionized. Only the neutral gas are only within the galaxies. We are really interested in this because first, the hydrogen is the most abundant element in the universe. It has 76% of barriers. And also it's primordial, so that even before star formation, you should be able to observe them. So this would tell us a lot about the epoch reionization. So the so-called 21 centimeter line is produced by the transition, the hyperfine transition in the ground state of the neutral hydrogen atom. So in the neutral hydrogen atoms, you see that the proton and the electron, they have a spin, and there depends on whether the spin are parallel or anti-parallel. You will get the slight difference, and if you have a spin sweep, you produce photons of 21 centimeter wavelengths. This is the so-called 21 centimeter line. But of course, there are the cosmic microwave background, which permeates in the whole universe. So actually, what you will be able to observe is the transitions of these photons together with the CMB. So you only observe its relative compared with the CMB. And on the other hand, of course, star-forming galaxies will produce, many galaxies will produce the Lyman alpha, Lyman beta, Lyman series photons, which can generate one of the atoms transit from one of the ground state to a higher state and then back. So this will change the occupation number for these two states. So what got me interested in this work in the first time was in 2003. I wrote a paper as a postdoc. I wrote a paper with Jordi Mirodi and Xuelei. We actually made a prediction that before the epoch reionization, when the first stars begin to form, we should have seen a very strong absorption here. So in fact, before us, people thought there is some absorption, but it should be relatively weak. And mostly people have been talking about using the 21 centimeter observation to look at the reionization signal, which are the emission signal here. But what we show is that, in fact, there could be a very strong absorption signal here. And also, if you actually look into individual stars, you will see that around this star there should be a sphere which shows this strong absorption. So why is that? So the fact is that this 21 centimeter signal given by this expression, now there is the, depends on, of course, the fraction of neutral hydrogen and also the density, the total density of the matter here. But then it's also dependent on what we call the spin temperature. Basically, this spin temperature gives the relative distribution of the neutral hydrogen atom in the two states. And the spin temperature, if it is higher than CMB temperature, you will see an emission signal. But if it's lower than the CMB temperature, it's negative, so you see an absorption signal. Now, as you can see from this expression, if you are looking at the emission signal, when the spin temperature is higher, is much larger than CMB temperature, you will get into basically a constant. So that saturates. So this is not very large. It's only, I think I missed the units, but it's only something like a 26 millikelvin in this standard units. Of course, this can change a little bit, depends on these other things. But if the spin temperature is much lower than CMB, you will get a very strong absorption. That's the idea. So how do you get the spin temperature lower than the CMB? So in fact, you can regard the spin temperature as a thermal system with very low capacity, heat capacity. So it interacts with the CMB, so the CMB will tend to make its temperature equal to the CMB temperature. But on the other hand, the collisions between atoms and the scattering with Lyman alpha photons will tend to make the spin temperature equal to the kinetic temperature of the gas. And if the kinetic temperature of the gas is lower than the CMB, then the spin temperature could be lower than the CMB. So we showed that when the first stars begin to form, it produces a lot of Lyman alpha photons, which can couple this spin temperature to the kinetic temperature. So that's why you produce this very, very strong absorption. You can also have some absorption during the dark age. That's because at that time there's higher density, so you have more collisions. And but then, of course, at these lower frequencies, the galaxy generates a lot more radiation, so it's harder to detect this signal than that one. So that's why it's getting me into this. Of course, this is very exciting, but in detecting it's very hard because when you are interested in this epoch reionization 21 centimeter signal, but then in front of you there are many other signals, what we call the foreground, The strongest coming from the galactic synchrotron radiation, but there are also the extragalactic radio sources and also the galactic thermal radiation. Now the galactic synchrotron radiation is about 10 to the 5 times strong than the signal itself. So it's going to be hard to detect it. Now in principle, these foregrounds are all very smooth in spectrum. So if you subtract the spectrum, the smooth component of the spectrum out, you should be able to find these 25 centimeter signals. But because this difference is so large, if you subtract it incorrectly, you will not be able to detect it. So it's very hard experimentally. Now, people started doing these experiments in both detecting what we call the global spectrum. Basically, that's the whole sky average of the spectrum, or the tomography, which is the anisotropy in the sky. So in the global spectrum, people have cited, for example, the AGE experiment have in 2012 published these limits on them. And also people have modeled, try to predict what the signal will look like. So in fact, there are many uncertainties in the star formation and the feedback, so you do not know really what will be the model, but you can set a number of parameters, and for each parameter you get one of these absorption curves. So you can see these absorption curves. The strongest signal in the extreme models will give something like 250 millikelvin absorption, whereas most of the models actually give much lower, maybe 50 or 30 millikelvin absorption. So people have been trying to look for these signals. So there are a number of such experiments. The most well-known is the AGE experiment, which also began the earliest. And but there are also the Sci-Hi experiment in Mexico, and Prism experiment in South Africa, and Saras experiment in India, and Big Horn in Australia, and finally the LIDA in the United States. So this year, the AGE experiment, which are done by the United States, but the experiment itself is located in Australia, claim the detection. So this is what they look like. So they have this antenna, which is a kind of a flat dipole on top of a ground plane, trying to observe the sky. So, of course, you have to take into account of a very careful measurement of the sky. So they developed a set of complicated calibration mechanism to both calibrate the response of the system, including the receiver gain, and also how the antenna, when the antenna transmits the signal into the receivers, some of these signals will be reflected back due to mismatch in the impedance. So they developed a complicated scheme of trying to measure them. And of course, you also have to be careful, because if you look at the sky, so this shows the sky brightness, at any moment, the antenna will look at a part of the sky, which is shown by one of these circles. As the Earth rotates, you see the sky moving across your beam pattern. You will see this. You will see different part of the sky, and you see that the different part of the sky will look slightly different. Now, of course, this is just showing one frequency. Now, if you are looking at different frequencies, now the antenna typically the beam pattern will depend on the frequency. So at different frequencies, you will also see different side of the sky. So if you're not careful enough, you will, because of you are seeing different part of the sky, that will get mixed into your spectral measurement. You will think you detect some spectral feature, which is really the difference in the antenna pattern. But anyway, so the AGE experiment took great efforts to take into account of these effects, and they claim this year to detect something. So here is that what you got the raw signal, which is, as you can see, quite large, a few thousand Kelvin. But when you're subtracting out the smooth components, you basically eventually get this absorption, which is about minus 0.6 Kelvin. So what is very interesting is that the frequency of this absorption feature, which is around 80 megahertz, corresponding to redshift 18, which is exactly where we expect the first stars begin to form copiously. So that's very exciting. Maybe we are seeing the cosmic dawn. But in fact, there could also be other explanations. The most disappointing one would be that you found this foreground contamination, or it's a problem of the calibration. But that we don't know for now, so we will need to wait other experiments to repeat and confirm this discovery. The theorists have come up with many interesting explanations. The earliest one is published by Wagner, suggesting that the baryons are colder than we expect. Because in fact, this signal, which is an absorption signal of about 550 millikelvin, is about twice the maximum load absorption. In order to get such strong absorption, you have to have the gas cooler than what model predicts. Another possibility, how do you cool the gas? So the idea is that you invoke the interacting dark matter. The dark matter is cooler than the gas itself, and when it interacts with the baryons, it will cool the baryons so that you get a cooler gas. Another possibility is that maybe there are some extra radio background in the early universe. So we usually think that the radio background at that time is dominated by the cosmic microwave background. But if there are some way to produce an extra background, which is quite large, maybe more than 100 Kelvin at that time, then it could also produce this stronger absorption. Although in order to have such a high radio background, you have to, the things which produce it must have very high radio loudness. So this is the dark matter, interacting dark matter model. In fact, you see, one problem with this kind of model is that if there is a strong interaction between baryons and dark matters, it will not change the cosmic microwave background anisotropy. I, in fact, wrote a paper in 2002 making constraints. Even at that time, the constraint is already pretty strong. So to evade this kind of constraint, Wagner suggested that the interaction cross-section is energy dependent. So that at high energy, it doesn't have a lot of interaction, but at low energy, it could have interaction. So that requires a light dark matter with a Coulomb-like interaction, which may be a hidden photon mediated by a hidden photon or milli-charged dark matter. So that's very interesting, and many people wrote papers, but currently I think already the current experiments, both from the CMB and other kind of particle physics experiments, already place very stringent constraint on that. And there are many other ideas. I think I will, due to limited time, I will not go into details of them. So let me say something about my own work on this field recently. One thing is a joint work with junior faculty in my group, Yilong Xu and Bin Yue. So we kind of look into this thing, see what is the expected absorption signal in the standard theory. So in models I showed you, the maximum is about 250 million Kelvin. Is that really true? But in fact, those models all assume the gas are basically uniformly distributed. So in fact, that's not true, because when you have an inhomogeneous distribution of the gas, now if the gas is just moving from this place to the other place, it doesn't change anything, because it still absorbs the same amount. But in fact, if you have inhomogeneity in the density due to the temperature density relation, you have a higher density place, the TK will be higher, so that it will produce less absorption. And now, of course, during the depolarization, there are very limited amount of the dark matter halos which have been produced. So that will not change the result. But then around these halos, there are this nonlinear gas. This gas hasn't collapsed into a halo, but it's already moving toward the halo. So they actually could change the picture. So we did a calculation. In fact, very interestingly, Bachner himself in 2002 produced an analytical model for modeling this kind of gas. So we used that model for calculation, and we found that, in fact, the absorption signal will be only 60% of the original one. So that's 40% less than expected. So actually the contradiction is even stronger. Now we are also doing a numerical simulation to get a more detailed result on this. Another thing is that now we try to look into the reionization history, because as the AGES experiment have been claiming results, maybe in the next few years other experiments to detect this anisotropy may also start to produce some results. So this is a simulation showing our understanding of the reionization process. At the high density regions, you begin to form stars, and these stars produce photons which ionize the gas around them. Now, of course, you can see this produce the ionized regions, which looks very localized, because initially all of the high energy photons will be absorbed by the gas around them, so that they produce only a finite size of these ionized regions, which we call bubbles. Now, as more and more of these bubbles begin to form and expand in size, they will eventually contact with each other and merge with each other. Then you kind of ionize the whole universe. Only with some regions you can see this kind of filament structures, high density regions where the gas is ionized, but then because it has higher density and the recombination rate is higher at that time. So this place will recombine to produce higher neutral density. So this is the basic idea of the model. But to model this is very complicated. You have to take into account of the star formation, the feedback, the retracing, transfer, and so on. So it's hard to do this kind of simulation. Because there are many uncertainties. Now, if you want to try all different parameter combinations, it's very hard. You can only maybe try one or a few of them. So people have been trying to model this and gain some physical insight using analytical models, or what we call the semi-numerical models. So the idea here is that this is again the gas from initially all neutral proceed to forming these bubbles, and more bubbles eventually form and ionize the whole universe. So the idea of this bubble model is that we can calculate at each point the balance between the number of photons required to ionize it and the number of baryons there. And the condition for gas being ionized is that this equation holds, or the number of photons bigger than the number of photons produced bigger than the number of photons needed. So how do you predict this number of photons? Now you can predict how many gas fraction are in the halos which are produced, and then you can calculate how many photons they produce. So this is so-called excursion size theory, which is basically you average the gas at each point with a different size of smoothing filters. Now, you find that with different smoothing filters, you will get at each point some trajectory corresponding to different size. And if you go to infinity large filters, of course you get this typical average density. So all of these converge to delta equal to 0 and on the largest scale. But then for each different place, this goes a different random trajectory. And you claim that it begins to form halos when it crosses a certain threshold. So those places where it first crosses the threshold produce the galaxy or star, and then it will produce the photons to ionize the place. So this is the idea behind the so-called bubble model. And people using the same idea to write what they call the semi-numerical models, showing how the evolution of the gas ionization process. But what we think, this model has been very successful and many people have used it to study the ionization. But we think the problem is that at the late stage of the hyperionization, this model is bound to fail. Because at that point, you see all of these ionized bubbles begin to overlap with each other, so that most of the regions, ionized regions are connected. So its basic premise is no longer true, because the photons are produced are no longer local, but are transported from other places. But in fact, you can correct this by using an alternative model, is that in the late stage, you treat these remaining neutral regions as what we call the neutral islands. These neutral islands are in regions with density density lower than the average density, so that these regions will have less photons being produced locally. And you can model during this time the photon balance equation. Instead of just the locally produced photons, you also have a background photons which coming from around them. Now, how many photons coming around them? Now you can calculate an average background flux and then multiply that with the surface area of your neutral island. So then you can again come up with an analytical model or semi-numerical model. Now there are some intricacies here, because in fact, if you look carefully, you found that within these neutral regions, which are quite large, there are also some smaller regions which could be have higher density, so they can still form photons, form galaxies and produce photons. So that this produce what we call the bubbles in the islands. The islands referring to the neutral region, the bubbles referring to the ionized region. So then you have to kind of dealing with this using the excursion set theory with two barriers, one for the normal barrier, another one for the so-called bubble in island barrier. So with this, this kind of modeling, we come up with an analytical model which can predict the size distribution of the neutral regions at different redshifts. And we also produced a code based on their original bubble model code called the 21 centimeter fast. We modified that part and produced what we call the island fast, and did this simulation and showing this evolution. So here is a movie showing the evolution using our model. As you can see, it's ionized, and then many of the regions remain neutral. If we run further down, this will be getting ionized, but we didn't go further. Okay, so let me switch one other thing is that we try to, now once you can predict this, how this evolution of the realization, how do you quantify them and compare the model with observation? So we look into the topology of the realization. This actually shows 4 different models. Each model have the from high redshift moving through to lower redshift. And how do you compare them? And if you observe them, how do you know that which one gives you the correct result? So we use the so-called 2D genus. The 2-dimensional genus is basically, you can consider it as the number of hot spots minus number of cold spots. And you got this, for these different models, you got this kind of genus curve. And you found that for each of them, these genus curves, the broad feature looks like, but they are in fact each different. So this can be used to compare it. Now you can move one step further, actually using the 3-dimensional case. And people have also have the tools called the Minkowski functionals. Basically, you found that these are in the 3-dimensional space. There are 4 independent Minkowski functionals: the volume and the areas of the surface, mean curvature of the surface, and the Euler characteristic. Basically, if you going through different density contrast, you will produce this different kind of contours surfaces or isodensity surfaces. Now, these surfaces, as you can see, at some extreme level, because the extreme are very small in number, they will be discrete. So you get this kind of picture. But when you are going to near the average density, they are all get connected together. So you get this much more complicated situation. And if you look at the Minkowski functionals, you plot them as a function of this nu, which is the overdensity divided by the standard variance. You get this Minkowski functional curves, and that gives you a tool to quantify them. So recently we are working on this, and this Xuelei Chen is an exceptionally bright undergraduate student who did this work during the summer of this year. So we produced this full Minkowski functionals through different redshifts. Because of time, I will just go into the results. So we see that we found that the stage, the reionization can be classified into 5 different stages. Initially, we will have ionized bubble stage, where you have very high neutral density, so the bubbles are indeed isolated. But then you will get into what we call the ionized fiber stage, when the fibers begin to connect with each other. Then finally, the ionized and neutral regions are kind of comparable and become a very complicated sponge-like state. And then, of course, more gas, more volume are being ionized. So now the neutral region have a fiber-like appearance. Finally, we go to the neutral island state. So these are the results we see. So initially, the neutral region are marked as transparent. The red are all ionized regions. But in fact, you can see these are individual ones. They are not connected. Now the blue one, showing the largest connected ionized region, this is still very small. But then you produce this very large cluster of them, which goes through the whole region. This is what I call the population of this system. Some people use a different definition, but I think my definition is more in line with the usual use, because people, when they talk about the population, it means they produce an infinitely large cluster. Now, what do I call the bubble overlay? Some people call it a bubble population. Is that all of these large ionized regions begin to connect with each other. They all merge into one huge cluster of them. Then we go into the sponge stage, where the neutral and ionized regions are all intertwined with each other. And then we move further down. You've got more ionized regions with less neutral regions, what we call the neutral islands. This shows the comparison of our simulation island fast with the standard one called the 21 centimeter fast, which doesn't have the take into the account of the effect we mentioned. So I think I'm almost running out of time, but let me mention a little bit about the experiment status. So currently there are many epoch reionization experiments going on, but none of them have detected yet because of this highly difficult foreground situation. So there are the LOFAR in Europe, the paper in South Africa, and 21 CMA in China, MWA in Australia, and HERA also in South Africa. So the paper is actually 6 operating. They are moving into the HERA. So now HERA in the future will expand into a very large array with very compact and regular configuration. Also ongoing is the SKA experiment, which SKA Low in Australia, which take a different philosophy of these different stations of antennas forming more irregular distribution. In addition to the epoch reionization, people are also trying to look into the mid-redshift. So in China, we have FAST, and also my personally leading what I call the Tianai experiment. So this experiment is located in Xinjiang in China, West China. And it's composed of 3 cylinders right now, and with 16 dishes. If it's successful, we hope to expand it into much larger scale, maybe 10 times the current scale. So this is the photo of the array. This is the dish array. This is the cylinder array, and we are taking data for 2 years now. Of course, right now we are not continuously taking the data. We only take some data and analysis and correct problem, and then take more data. Finally, we are also doing some kind of space-based experiment. This is the experiment which I'm involved. We try to, so at very low frequency, especially below 10 megahertz, the ionosphere of the Earth will absorb the signal, so that radio signal. So from the ground, you cannot really see below 10 megahertz. Now, above 10 megahertz, but maybe below 50 megahertz, maybe even below 100 megahertz, you are still affected by the refraction of the ionosphere, and as well as the electromagnetic interferences. So if you can go to the space, you can avoid these problems. Especially, you can use the moon to serve as a shell. You can go in around the moon so that you take the data in the back side of the moon, and when you move into the front side of the moon, you kind of transmit the data back. So we are carrying out an intensive study on the design of such an experiment called the Discovery Sky at the Longest Wavelengths. So this consists of one larger satellite with 5 to 8 smaller satellites in the same orbit, so that they form an interferometer array, and as it circles around, it will take more and more data and generate more baselines. At the same time, it also measures the global spectrum. So hopefully that will be useful to both look at this new window of spectrum that people have not get any good quality data so far, and also make a more precise measurement at the cosmic dawn. So that's my talk. Thank you very much.
Professor, the 21 centimeter radiation. Right now, I think because of the cosmology redshift, there are many didn't exactly things.
Yeah, we call it 21 centimeter. It's actually redshifted 21 centimeter. It's no longer 21 centimeter. So, for example, if you are the photon is immediately redshifted at 10, so now you will see it at 21 times 11 centimeter. So yeah.
Okay. Then could you give me the exactly reason why it's so difficult to detect the 21 centimeters radiation? You said there's many noise. Could you tell me the range of that?
The main difficulty comes from the foreground, because the galaxy, the Milky Way galaxy, and the other radio sources produce much stronger radiation than the 21 centimeter signal. So when your telescope look at one direction, most of the energy you receive are actually not from this signal you are interested in. It's from the things in front of it, which is what we call the foreground. So the foreground is much stronger in the sense that it's maybe 10 to the 4 to 10 to the 5 times stronger than the signal itself. So you have to be carefully remove this foreground in order to see the signal. Yeah, so that's why it's very hard.
Okay, thank you.
Okay, the last short question. Hi, Felix. You mentioned the 3 Chinese experiments observation. So what they are doing, what's their schedule? Looks like the FAST become a tourist attraction other than scientific sort of things. Okay, can you tell us more?
So right now in China, The FAST, first of all, is a general facility. It doesn't only do 21 centimeter. It's all kind of different things. Currently, most of its effort is dedicated to pulsar search, but hopefully it will also start a general survey, including both pulsar and the 21 centimeter signal. Now, it does attract a lot of tourists, but on the other hand, they kind of place a radio quiet zone so that the tourists have to first go to a tourist center and hand in all of their electronics, including the cell phone and the camera and the watch, and then they take a bus to the site for the visit. So it's not ideal, but it's in a controlled fashion. Now, the other two experiments are more dedicated to 21 centimeter. One is what I lead. We are running, but we are not there yet. Another experiment is led by Professor Wu Xiangping, also in our observatory, also in Xinjiang. Their experiments have been running for maybe 10 years or even longer. They produced some results, but they did not detect the 21 centimeter signal. And there are a number of limitations which why they didn't detect. But anyway, so that's the situation. I think right now they are now shifting the focus more to trying to use such a technology to detect the neutrino, high energy neutrinos. Yeah, so that's what I know about.
So yours, when you expect a scientific result, your antenna, when you expect some sort of scientific result?
It's going to be hard. So we think next year we will probably write a few papers showing the tests we observed, we got on the data. But I think we are still very far from detecting the 21 centimeter. And one problem for our array, the 10-light array, is that our array is very, very small, so that it doesn't have a high resolution. So except for doing the 21 centimeter, it's going to be difficult to produce competitive results compared with regular telescopes. One thing we think maybe is, in addition to 21 centimeter, one thing it may be useful is to detect transients such as fast radio bursts or the electromagnetic counterpart for the gravitational wave events. So we are currently trying to upgrade the receiver system to have a higher time response to capture the fast radio bursts. So in fact, as you know, a similar experiment in Canada called CHIME already detected a number of fast radio bursts. And we are trying to do the upgrading and do the similar things. But unfortunately, we don't get much. We proposed to do this 6 years ago, but we only got the first batch of money this year. So, so it's on hand. Yeah.
Sorry, yeah, the talks are so good, but we have to stop here. And let's thank the three speakers in this afternoon session. And next, Buddha will take a photo.